Hey everybody, I hope you enjoyed the first video about electron configuration. This is going to be the second video, and it's going to focus specifically on how to draw the electron orbital diagrams and write the electron notation. Let's review the main two learning targets of this lesson. Learning target 1, I can use the periodic table to determine the location of electrons, energy level, sublevel, and orbital in an atom, and write the electron configuration to demonstrate this knowledge. So in this video, I'll go specifically of how to write that electron configuration, and that involves using the correct notation. The second learning target is I can use the Aufbau Principle, the Pauli Exclusion Principle, and Hund's rule to draw an electron orbital diagram of an element. This video will go into all the details about each of these rules and how they apply to the electron orbital diagram. So let's take a look at the first rule. The first rule is called the Aufbau Principle. The Aufbau Principle states that electrons fill lower energy orbitals before they fill higher energy orbitals. This seems almost common sense, right? That things should be lower energy before higher energy. But that's not necessarily the case. Electron configurations have a very unique order, and it's explained by the diagram on the right. So let's take a closer look at that diagram. Take a look at where it starts, right? It starts at 1s, then it goes to 2s, 2p, 3s, 3p, and then it jumps to 4s. So let's investigate what's really going on there. In the diagram on the right, follow the diagonal lines to determine the correct order from low energy to high energy. This is called the diagonal rule. So the correct order of increasing energy is going to be the following list, okay? So give me a moment to really explain how the list goes. Let's follow this diagonal line. 1s is where we're going to start. Think back to a Bohr model. That 1 is referring to the Bohr model. And it's actually written right here. Each letter N refers to the energy level on the Bohr model, okay? So the first energy level only has an S sublevel, and that's where it starts. If an atom is on the second row of the periodic table, it moves to the second energy level. So then it goes to 2s. And let's keep following this diagonal line. The second energy level has an S sublevel and a P sublevel. The third energy level has S, P, and D. But let's hold on a moment. Really follow that diagonal line. 2P to 3S. This diagonal line then goes up to 3P. But if you follow the diagonal line, it doesn't go 3P all the way to 3D. Do you see that? It actually goes from 3P to 4S. So this is a unique characteristic of electron configurations, and that's why the Aufbau principle is important, because we really have to understand what's a low energy versus high energy. So we go from 3P to 4S, and then from 4S we go all the way to 3D. So 4S has a lower energy level than 3D. Then let's keep following. It goes 4P, then 5S. So kind of see where the arrow's going. And then we jump to 4D. So 4D, 5P, 6S. And then 6S, we jump all the way to 4F. And then it goes to 5D, 6P, and 7S. 5D, 6P, 7S. Let's see if I have enough room to fit everything in there. From 7s, we go all the way to 5f, and then 6d, 7p, and 8s. So this would be the correct order of the energy levels and orbitals. And it's not a clear just you fill the first energy level first, then you go to the second energy level, then the third. You have to fill the sub-levels first in the correct order. So why does this occur? Why does the diagonal rule exist? Well, we can attribute this to many things in electron configuration. It goes all the way back to quantum mechanical model. Remember that equation I showed you briefly, the Schrodinger equation? All that crazy math that you would do in higher level chemistry or physics, that would explain why the diagonal works the way it does. So we don't need to go into the crazy math. We just need to know the correct order of the energy levels and the sublevels. All right, let's finish out the last few sentences here. So each n refers to the energy level on the Bohr model, which also refers to the row or period on the periodic table. So remember that if an element is in the second row on the periodic table, that means that it is going to have electrons that go up to the second energy level. And if it goes up, if it's in the fourth row, that means that it will have electrons that go up to the fourth energy level. There are only 7 rows on the periodic table, but the Aufbau principle is hypothetically possible for future undiscovered elements. So this diagonal rule that you see here only goes up to 8s, but theoretically we could just keep going higher and higher and higher. But right now, the periodic table doesn't go that far. All right, so this is the first rule, the Aufbau principle, and it states the correct order for going from lower energy orbitals to higher energy orbitals. After reviewing the Aufbau principle, we're now going to move on to the second rule, which is a little bit more simpler. This one is called the Pauli Exclusion Principle. The Pauli Exclusion Principle states that electrons in the same orbital must have opposite spins. So, what do we mean by this? If you remember when I first gave you an example of oxygen in the previous video, oxygen has 8 electrons, and I drew a box to represent the orbital. So the box represents the orbital. And then the arrows are going to represent electrons. On the 1s sublevel, oxygen has 2 electrons. I'm going to draw 1 going up and 1 going down. That is to satisfy the Pauli Exclusion Principle because it states that the electrons must have opposite spins. What are spins? Well, that's kind of a more complicated electromagnetic explanation for what an electron spin is. For now, just think about it that electrons like to be balanced. So they like to hang out in pairs, and they like to be balanced. So one is going up while the other is going down. These, depending on the arrangement of spins in an element, it actually could relate to the metallic properties or the magnetic properties of some elements. So far, we have reviewed the Aufbau principle, the Pauli Exclusion Principle, and now we're moving on to the third rule, which is called Hund's rule. Hund's rule states that electrons fill empty orbitals on the same sublevel before doubling up. For example, electrons on the p sublevel will separate on different orbitals before they pair up. So what does this look like? Let's go back to oxygen. Like I said, an oxygen atom will have 8 electrons. On the 1s sublevel, there is one orbital there. Because it's an s sublevel, s always has one orbital. Let's go to the 2s sublevel. Same thing. It's the second energy level, but it's an s sublevel, so there's only one orbital there. Then let's look at 2p. If you remember from our information on atomic orbitals, a p sublevel will have 3 orbitals. So I'm going to draw 3 orbitals here. These 3 orbitals are all on the p sublevel of the second energy level for oxygen. Now I have 8 electrons to play around with for oxygen, and let's see how they would fill this electron orbital diagram. One electron starts at the 1s sublevel, and then we're going to fill this orbital here. When I move on to the second energy level, we're going to do the same thing. But once I move to the 2p sublevel, this is where Hund's rule plays a role. So Hund's rule states that electrons fill empty orbitals on the same sublevel before doubling up. Whenever we have an s sublevel, there's only one orbital, right? So Hund's rule doesn't really play a role. But on the 2p sublevel, there are 3 orbitals. So what that means is that these electrons are going to separate before they pair up. So far, out of oxygen's 8 total electrons, I've used up 2 on 1s, I've used up 2 on 2s. So how many more do I have left? I have 4 electrons left. Let's see how they would be positioned on the 2p sublevel. I'm going to fill this orbital first. Then I'm going to move on to the next orbital, and they have to be the same spin. So we're going to start with an up spin. I can fill another level there. How many electrons have I used so far? I've used 1, 2, 3, 4, 5, 6, 7. 7 electrons. Oxygen has 1 more electron to place. Now I can pair up that electron on the first orbital of the 2p sublevel. This here is the proper electron orbital diagram for oxygen. Now that we've drawn the proper electron orbital diagram, let's take a look at what the notation would look like. So notation is just writing out, or writing a list almost, of all of the orbitals and sublevels. So we start off with 1s, and there's 2 electrons on the 1s sublevel. So I put a 2 right there. It looks like an exponent, but it's not. It's just a superscript that's referring to how many electrons are on the 1s sublevel. Now let's look at 2s. 2s comes after 1s, and how do I know that? That goes back to the Aufbau Principle. That tells me the correct order of all of the orbitals. There are also 2 electrons on the 2s sublevel, so I put a 2 as a superscript right there. And now I have the 2p sublevel, so I'm going to write that. And the 2p sublevel has 3 orbitals, but when it comes to the notation, we don't have to signify the different orbitals. We just have to write how many electrons there are in total. So there are 4 electrons in total on these orbitals here for 2p sublevel. So I'm going to write a 4 right there. If you add up all of the superscripts, if I add all these numbers up, 2 plus 2 plus 4, it should equal 8 electrons, which is the total number of electrons in oxygen. Go ahead and take a pause. Make sure you write this down somewhere so that you have it, and then we'll do some practice problems together. So we just reviewed the 3 main rules of electron configuration. Aufbau Principle, which tells us the correct order of all of the orbitals and sublevels. Pauli Exclusion Principle, which tells us that electrons have opposite spins. And then the Hund's rule, which tells us that electrons like to separate first before they pair off. So let's do a problem together. Let's take a look at fluorine. So first, I want everyone to draw a fluorine Bohr model. You can pause this video right now and draw a Bohr model of fluorine right now. So this is what your Bohr model should look like for fluorine. If you remember, fluorine is going to have 9 electrons. How did we determine that? Well, we had to look at the periodic table. Since we're talking about atoms, atoms are neutral, so the number of protons will equal the number of electrons. Fluorine has an atomic number of 9, so that means it has 9 protons, which it also is going to have 9 electrons. Determine the number of energy levels in a fluorine atom. Well, it has 2 energy levels because it's on the second row in the periodic table. Both of those pieces of information help us determine the Bohr model. So I drew 2 circles around the nucleus. The first energy level can fill up 2 electrons there, and the second energy level can fill up a total of 8. But fluorine only has 9 in total, so 2 fill the first and 7 fill the second. The Bohr model helps us a lot, but it doesn't tell us the more precise location of where the electrons are, and that's where electron configuration will help out. I'm going to write out the electron notation first, because that might be helpful before we draw the electron orbital diagram. So in order to write the electron notation, we have to remember the rules. Remember the first rule, the Aufbau Principle? We have to follow these, we have to follow the diagonal lines to have the correct order of the sublevels. So let's write a few out. Let's say I have 1s, 2s, and we can go all the way up to 2p. Why do I know? How do I know I'm able to go up to 2p? Well, fluorine has 2 energy levels, right? So that means I want to write out all of my sublevels all the way up to 2p. And then I can start filling in my electrons. So 9 electrons in total. How many electrons can fit on the 1s sublevel? The answer is 2. Because s has 1 orbital on it, and 2 electrons fit into 1 orbital. Now let's look at 2s. How many electrons can fit on there? Also, 2 electrons can fit on there. Because it's a s sublevel, there's 1 orbital. Now 2p is a little tricky. Remember, 2p can go up to 3 orbitals. All right, so a p sublevel can fill all the way up to 6 electrons there. However, fluorine only has 9 in total. So I used up 2 right here. I used another 2 here. That's 4. So that means I have 5 left. So it's 2p5. Now, what does this look like for the electron orbital diagram? One s is first. Instead of drawing a box, if you just want to draw a line to represent the orbital, that's fine too. You will also see some references and different sources on the internet that might actually use a circle to represent the orbital, and it will draw the electrons inside there, just so that you're aware in case you see different resources that have slightly different images. I will either be using a box or a line to represent the orbital. So I have 1 orbital on the 1s sublevel. Then I have the 2s sublevel. I also just have 1 orbital. Now I have the 2p sublevel. I have 3 orbitals for the 2p sublevel. So I'm just drawing lines. It's a little bit easier to draw them. Now that I'm on my electron notation, I determined the number of electrons for each sublevel. Now I'm going to draw them. The 1s sublevel, I have 2 electrons. You'll also notice that I drew a half arrow. There's really no difference between a full arrow or a half arrow. Once we're drawing a lot of electron orbital diagrams, I will draw the half arrows just because it's a little bit simpler. There's no actual difference. Either or is acceptable. So 2 electrons fill the 1s orbital. 2 electrons are going to fill the 2s orbital. Now I have 3 orbitals on the 2p sublevel. Well, if I look right here, I have 5 electrons, right? So I have to fill these 5 electrons on here. Also, if you'll notice, I put 1 electron going up and 1 electron going down. That's due to the Pauli Exclusion Principle. Now let's try to fill the 2p sublevel. I have 5 electrons that I need to draw there. 1, 2, 3. So take a look. I want to separate them first, right? That's because of Hund's rule. Hund's rule says that electrons separate before you pair them up. That's how you should draw them as well. I have 5 electrons on this 2p sublevel, but I want to separate them out first. So 1, 2, 3, 4, 5. So once all those orbitals were filled up with 1 electron, then I can pair them up with a second electron. A really good analogy for this is, imagine that you're on a bus, right? So if you're ever on a public bus, do you usually sit next to a stranger on a bus? No, you usually find your own seat. Well, electrons are really similar. They want to find their own seat first before they start to pair up. So that should help you remember Hund's rule. So this is what your answer should be like for each of these parts here. The Bohr model should look like this, the electron notation should look like that, and the electron orbital diagram should look like this image right here. Also on this part, I would like you to label the parts in the drawing. So what does 1 refer to? 1 refers to the energy level. What does S refer to? That refers to the sublevel. And what does the superscript refer to? That refers to the number of electrons. So go ahead and do that for the other parts of these drawings, and then we can move on to the next example. The next example here is helium. So I would like you to do the same thing. Draw a Bohr model, draw an electron orbital diagram, and then write the electron notation for each of these. Go ahead and give yourself a little bit of time to do that. You can pause the video now. All right, as you can see there, that is the Bohr model for helium. You'll also see that I wrote the number of electrons for helium. Determine number of electrons in a helium atom, 2 electrons. In the total helium atom, there's only 2 electrons. Determine the number of energy levels in a helium atom. There's only 1 energy level for helium. It's on the first row. So the Bohr model is really simple. You'll also notice that I just kind of shaded in the nucleus. We don't really need to worry about the nucleus right now. We're just looking at the electrons. So in the Bohr model, we see 1 energy level, and there are 2 electrons on each of them. All right, go ahead and write out the electron notation and the electron orbital diagram. Now you can see the correct electron notation for helium. It's pretty simple. It's just 1s2. So how did I know it was going to be 1s? Well, I have to look back at the Aufbau rule, and I look at the diagonal chart. I always start at 1s. Helium only has 2 electrons, so I'm just going to fill those 2 electrons in the 1s sublevel there. And I also know that an s sublevel only has 1 orbital, so that orbital is totally filled. If you haven't already, go ahead and draw the electron orbital diagram for helium. Now you can see the electron orbital diagram for helium. It's also pretty simple. I just write 1s, and then I either draw a line, or as I did in the other images, you could draw a box for the orbital too. Either or is acceptable. Now, drawing the orbital diagrams are usually a little bit easier once you've identified the electron notation. Sometimes, though, you might want to draw the orbital diagram first. Whichever you prefer, it's totally up to you. The orbital diagrams are a little bit more visual, so sometimes it's nice to draw them first, but then other people like to write out their notation first so they know exactly how many electrons are in each of their orbitals. So these are the correct answers for helium. We can now move on to our next example. The last example I have for you is titanium. Go ahead and draw a Bohr model for titanium and attempt to draw the electron orbital diagram and write the electron notation. Make sure you determine the number of electrons and the number of energy levels for titanium. Remember, Titanium's actually going to be a little bit hard, especially for the Bohr model. We're going to kind of figure out why the Bohr model isn't all that great with this example, but go ahead and attempt that right now. Okay, so titanium has 22 electrons, and it goes all the way up to the 4th energy level, and I determined that information from looking at the periodic table. So here's what a Bohr model could look like for titanium. I have 2 electrons on the 1st energy level, 8 on the 2nd energy level, and I have 8 on the 3rd energy level as well, and then 4 on the 4th energy level. But this doesn't totally make sense. So remember I said that in Unit 1, the 3rd energy level can hold actually all the way up to 18 electrons, right? But some of them only want 8 electrons on the 3rd energy level. And titanium didn't qualify as one of those exceptions. So if I'm filling up all these energy levels on the Bohr model, the question becomes, what do I do with these last 2 electrons here, right? Do I put them on the 3rd energy level? Or are they going to go on the 4th energy level as I already have them? The answer is it's not clear cut, right? Because the Bohr model is incomplete. It doesn't tell us the whole story. So there's no real correct Bohr model for titanium. This is when electron configuration becomes a better way to analyze the arrangement of the electrons in an atom. So if you haven't already, go ahead and attempt the electron notation and the electron orbital diagram for titanium. I'm going to break down the electron notation for titanium in detail for you so you really understand what's going on here. So remember, in order to write out the electron configuration, we have to follow the diagonal rule from the Aufbau Principle. We start with 1s. I'm going to go ahead and write 1s. Then we go to 2s. 2s. Oop, I put a 2 there. I don't want to do that quite yet. So don't write the superscripts yet for the electrons. Just write out all of the energy levels and the sublevels. So 1s to 2s. Then I go to 2p. If I follow this diagonal line, I go to 3s. From 3s, I jump up to 3p, but this is where things start to get different. When I go from 3p, right after 3p is actually 4s. So 4s comes before, so if you follow that diagonal line, it takes you all the way, oh, my phone went off. That's okay. So if I go from 4s all the way to 3d, that is going to be the correct order there. So this kind of shows how the Bohr model doesn't get the full picture. The electron notation really tells us the correct order of all of the energy levels. All right, so remember, titanium goes all the way up to the 4th energy level. So that means I want to write my electron configuration somewhere up to 4. Now, it's a little hard at first. You may not know exactly if we go all the way to 4p, 4d, or 4f. Just take it step by step, okay? Write out a few energy levels and sublevels first, and then you can start to fill in how many electrons you have on those sublevels. All right, I have 22 electrons in total, right? Let's start to fill them up. 1s, I have 2 electrons there. 2s, I'm going to have 2 electrons there. So these are the superscripts that go right above the sublevel on each of these notations. 2p, the p sublevel can fit up to 6 electrons. I have 22 in total, so I got plenty of electrons to use. And then I have 3s, can fit up to 2. 3p can fit up to 6. 4s, well, let's see where I'm at. So I have 2 plus 2. So I'm getting these numbers from the superscripts. Plus 6, plus 2, plus 6. How many do I have here? 2 is 4, 10, 12. I have 18 so far. So I've used up 18 electrons. I have 22 in total, so I have 4 more that I need to place. Well, 4s, even though this s sublevel is on the 4th energy level, it can still only hold 2 electrons. So I'm going to put 2 in there. So if I add another 2, now I have 20. Again, I have 22 in total, so where do the last 2 go? I'm going to put them on the 3d sublevel. So this gives us a much more accurate picture of where the electrons are than the Bohr model. The Bohr model kind of doesn't work for elements like titanium that have a large number of electrons. Okay, so this is the correct answer for the electron notation. If you haven't already, draw the electron orbital diagram and I'll give you the answer in just a moment. Now I will explain how to get the electron orbital diagram for titanium. So I have drawn out all of my orbitals and sublevels there. I drew them from increasing energy. 1s is the lowest, 3d is going to be the highest here. And I got that order from the Aufbau Principle. So I have 22 electrons in total. I'm going to show you how to fill in each of these electrons here, okay? First, 1s, that orbital can fill 2 electrons. So I put 1 electron going up and the other going down. 2s can also fit in 2. 2p has 3 orbitals. When I draw these, I want to separate them first. So get in the habit of separating these electrons first, and then you can pair them up. How do I know how many go on each of these electrons, on each of these orbitals? Well, I determined that over here. 2p has a 6 in my superscript, so I know I'm going to want to draw 6 electrons in 2p. Now if I move to 3s, I have 2 there. 3p is also going to have 6. And then 4s, I'm going to draw 2 right there. Now 3d, this can be a little tricky here, okay? So 3d only has 2 electrons. Remember, I want to separate them first before I pair them up, which means I'm going to have 3 empty orbitals for titanium. You still want to draw the empty orbitals. Even though they're not filled up, you want to draw them. That's really important. The fact that they have empty orbitals, that means when we start talking about reactivity, they might actually share or transfer electrons with other elements there, and those electrons start to fill the empty orbitals. So even though 3D only has 2 electrons, for titanium, we want to make sure that we draw all of those orbitals there. So these are the correct answers for titanium. I'm sure that you guys will be working on this, and if you're struggling with this right now, that's totally fine. Do your best to understand this, and please ask questions. I'd be more than happy to work with you guys on whatever questions you might have on this. All right, I'll see you guys later. Bye.